Welcome back to ECE 320A. Unit 7 we're finished, but it will be on exam number 3, and exam number 3 is a week from today. Just as a reminder, the next time that you have the option of seeing me in a class type relationship is Monday for office hours, and those have been changed. So don't come at 4 to 5 next Monday. I've been pushed somewhere else. So I'll be somewhere else at that time, but I will be in the office from 2:30 to 3:30 on Monday afternoon. That's the 15th. Homework number 8 is due the following day on a Tuesday, and we will meet again, and we'll actually have a class and a review session on that Tuesday leading up to Thursday's exam. What I want to do today is first give you a quiz, and that's concerned with steady state behavior of the output. And steady state can involve a lot of different, in this particular curriculum or in this discipline, we talk about a steady state behavior due to a constant excitation or input, and also about sinusoidal steady state. So when we say steady state, you kind of have to ask, what steady state are we in? Are we oscillating at a particular sinusoid, or are we talking about having a constant input? And we'll then look at finding, after the quiz, the sinusoidal steady state. That's the SS part of this. Or you could just say it's steady state, but most of today after the quiz is going to be focused on sinusoidal steady state, and we'll try to derive that. And I know that you are really enjoying your MATLAB material, so I wanted to make sure that we put a little MATLAB into this class so that you could understand or see visually what's going on when I start talking about what's the output look like in sinusoidal steady state. We can generate that rather quickly with MATLAB. And we'll derive the strategy for applying these concepts in a sinusoidal steady state fashion. You won't have to rederive that on an exam, but I'm hoping it gives you a feel for where in the world does this expression come from. And if we have time, we'll look at some examples of finding that sinusoidal steady state in a circuit and in a transfer function. And then prior to exam number 3, we want to make sure that we understand how to find this h of j omega graphically. Bode plots is going to be, I use probably a lot, but it doesn't need to be used here. Bode plots will be on the final exam and not on exam number 3. But that's kind of the flow of information in terms of where we're headed. Once we have Bode plots, we'll get into filter design. And that's probably where we will finish the semester. Here's our quiz. I'm going to give you an input, X. It's going to now be influenced or injected into a system, and I hope that you can see by just inspection of that transfer function what that system can be thought of as. It's a low-pass filter, and then I'm going to ask you, what is the steady state output? Why? That's the quiz for different types of input signals. You're given a system. Now I'm going to hand you a signal, X, and you're going to keep that as, or use that as the input, and then you should be able to tell me what's the output. Here's the first one. What if X of t, the input to this low-pass filter, is e to the minus 2t? What's the steady state value of the output y? And I want you to start gaining some insight. If somebody calls you and they're interviewing you on the phone and they ask you this kind of a question, they say, low pass filter an exponential waveform. What's going to be the output from that low pass filter? They might ask something like that. How would you respond? Do we have to turn in a paper? Will you work on it if I say yes, or will you not work on it if I say no? So if you're working on it either way, I'm not going to collect it. So you can keep this in your notes, but I say quiz just to kind of get you going. To turn up your heart rate, yeah. Wake you up a little. Make you shake, yeah. Yeah. And we're not even hitting it with the sinusoid, and you're already shaking, but you are moving a little bit if you've hit it with an exponential. So this quiz could be an impulse excitation. We're initializing the energy storage pieces in your body, and then, I don't know, how long is your transient? What's your time constant? Okay, so here we are. X of t. What is the final value, or what is the steady state value of y? Can you see what is happening? Does anyone have an answer? Pardon? Decay? Are we in a dentist office with decay? What? This is an exponential decay, isn't it? And that's what you're exciting this low-pass filter with. What would you expect to happen to an exponential waveform that you low-pass filter? Did you have a question? That's supposed to be a 2. That's an exponent of 2. So where would you, well, maybe I'm going a little too quick. Where would you expect to end up? The dentist office answer was correct, right? You're going to have decay. And after a long time, where is x of t going? 0. So you're hitting a low-pass filter eventually with 0. You low-pass filter 0. What would you expect to get out? 0. So your final value, or your steady state value of y, better be 0 in this case. You bump it with an exponential waveform. You low-pass filter that, but eventually you're going to be at 0 for an output. What I was hoping you could kind of quickly say is that y steady state is 0 for this input. And now you could try to justify that. Here, the justification could be, let me give you the total response. Let me find capital Y of S and then inverse Laplace transform, which isn't too difficult given this input and transfer function as a low-pass filter. What's capital H of S? It's right there on the board, isn't it? It's 5 over S plus 5. That's the transfer function. What's the capital X of S? So you have to Laplace transform X of t. Shift happens, doesn't it? We had the t-shirt that said shift happens. Have to remember you have the right spelling. S-H-I-F-T. We're in a family show here. So shift happens, and we can Laplace transform. And what's the Laplace transform of e to the minus 2t? 1 over s plus 2. Here is capital Y of s. Now you immediately know the structure of y of t, because you can use the cover-up method to try to find a sub 1 and a sub 2. Pretty quickly, actually, in this case. You cover up this s plus 2. I can't do it on the video, but you can virtually cover up this s plus 2 factor in y of s and solve for a sub 1. You plug s equal to minus 2 into what's not covered up, and what do you get? Or what results? What is a sub 1? We cover up s plus 2 and we evaluate what's left at s equal to minus 2. Hurry, I'm going to cramp. 5 over minus 2 plus 5. 5 over 3. So this a1 is a little bit less than 2. What's a sub 2? Well, now we cover up the s plus 5 because we've multiplied that factor through on all terms, and we're evaluating then at s equal to minus 5. Now we have minus 3 in the denominator dividing into 5. A sub 2 is minus 5 over 3. Now you can take that into the time domain. You now have 5 over 3 e to the minus 2t minus 5 over 3 e to the minus 5t. That's the total response. And if you wanted to know what happens for large values of time t, they're both going to 0. They're both decaying exponentials. How long will you have to wait before you no longer see anything? What are the 5 tau, but how many time constants or how many modes do we have in this y of t? 2. And which one would last the longest? Or which mode lasts the longest? In this exponential form, I hope it's clear that e to the minus 2t lasts longer than e to the minus 5t. The time constant for this first mode, e to the minus 2t, is what? What's the tau for e to the minus 2t? Or you simply say 2 times what will give me 1? 1/2. So this is 1/2, and so we wait 5 of those. We wait 2.5 seconds before that one's gone. This one, we say, well, what would make the exponent equal 1? 1/5. The time constant now is 0.2 seconds. 5 of those is 1 second. This one is gone in a second, the second piece. This piece is gone after 2.5 seconds. And if you sketch it, that's maybe a lousy sketch, but you can sort of see that the top one is the e to the minus 2t with a 5 over 3 scaling factor, positive. The other one was a minus 5 over 3, decaying at e to the minus 5t. It should be finishing after 1 second. And the top one, the first term, finishes after 5 tau, which was 5/2. And what happens at the very beginning, at 0? 5/3 minus 5/3, so we're starting at 0. This bottom one is taking more away than the top one, but then after it finishes, basically after 1 unit of time, all you're really seeing is what's left in the first one that we had on the expression for y of t, the 5/3 e to the minus 2t. And again, this is verifying that after a long interval of time, you see nothing. You see 0. Questions on that? What is this? This is now a low-pass filtered exponential. Question?
If you had a question like this on the test, or like find the steady state and give it justification, could we just say, oh, it's 0 because we know that x and t is exponentially decaying, or do we have to go through all of the math to show that?
The question was, if we're faced with this on an exam, how much do we have to provide for our answer? One is you want to give me the correct answer, which is 0. The other is maybe based on how much time you have remaining. But you could say x of t is going to 0, and we're low-pass filtering that final value. It's going to be 0. You wouldn't have to go through every step that we've gone through here, but I'm trying to use this somewhat as a way to review what you know and say, oh, how would I approach this problem or this question based on my understanding of the material? How could I verify in my own head why this is true? Instead of me just saying, oh, it's 0, you're going, I have no idea where he got that. Well, now I hope you do after this discussion. But my answer was pretty vague to the question, but I think you could, it depends really on what's asked in the question. You know, justify with the total response. That could be part of the phrasing of the question. Or I could say it maybe is multiple choice, and what is the final value? That was the first part of the quiz. Here's the second part. If x of t is now 6. Pardon? Now what is the answer? What is the final value of the output? Question? Pardon? Oh, you're showing me a wildcat, or are you showing me a 0? Showing me a 0. How many think it's 0? We're putting in 6, and we low-pass filter it. How many think it's 0? Show of hands. A few of you. Why are you thinking it's 0? Because it's not changing? So is this exponential? No. The mode, what's the mode here? It's constant, isn't it? It's DC. And if this is now DC, how would you think to, or if you now think, oh, I'm low-pass filtering a DC waveform, DC is 0 frequency, how does that system behave at 0 frequency? How does a low-pass filter behave at DC in this particular case, for this filter? How do you find that? How does this system behave when S is equal to 0? It's 5/5, isn't it? Which is 1. So this is going to scale our input by a value of 1 in the final value, or at the final end result in steady state. So this one should be, whoops, I didn't want red, is 6. You've injected 6, and you haven't quit hitting it with 6. You just keep hitting it with 6. And does that 6 have much frequency content? No. You're low-pass filtering something that's not changing, so you're basically seeing what you're injecting. So how could we explain this? Let's explain it a little differently this time. Here is our transfer function in terms of a pole zero diagram. We just have one pole, and we have a numerator that doesn't have any zeros. There's no finite value of s that causes h of s to vanish. The numerator is simply a constant of 5. So whatever we do, whatever other contributions that system gives us, we still always have to keep that 5 upstairs in mind, or we keep track of it. But now, where is DC in this S-plane? And I have to thank whoever's putting these tents on the mall. They just keep them out there most of the semester. So now I'm hoping one of these days I'm going to see students walking underneath all those tents, and I'm going to be going, yep, they're in 320. They're evaluating the frequency response of that system. Where do we stand if we're looking for DC in this S-plane? Right here. That's where we're standing at s equal to 0. That's DC. And what's the contribution this pole makes at DC? Well, it's basically how far away am I from that point in the S-plane. That's how s plus 5 is, that's what it will contribute. That's what the pole will contribute at DC. So in this case, we said we had to keep track of the numerator. And now we need to measure this distance from here to the origin, from the pole to the origin. And what's that distance? 5. And that's what's actually down here. This distance is 5. Let me make this so you know which corresponds with what. And what does that give us then? That's our DC gain of the system, and that's equal to 1. How long do you have to wait for that to DC gain? Or so now what you can think of is you could say, oh, my y steady state is actually h of 0 minus times the magnitude of my input, which in this case was 6, or the value of the constant. And that's 6. So we're shaking the system with an input that doesn't shake. So we're asking, how does this system respond at DC when s is equal to 0? And we can figure that out by saying, well, what poles and zeros do we have, and what contribution do they create or influence? How do they influence our response? Well, the pole is going to give us a factor of 5 at DC contribution. The numerator started and remains at 5, so at DC we have a DC gain of 1. How long to wait until we can basically say we're there, we're at 6? Do we have, oh, well, this is, final value theorem says t goes to infinity. We have to wait forever, Dr. Tharp. Really? In reality? How quick do we get to 6? 5 tau. What's tau? X of t didn't have any tau in it, did it? I'm trying to confuse you. What do we have? We have a constant that we're applying to a system. What's the impulse response of that? Go back to your convolution. And you say, what happens when I low-pass filter a constant? That was one of your supplemental videos to look at. or to examine. What happens when you low-pass filter a constant? You do have the influence of that impulse response. What's the impulse response look like? 5e to the minus 5t. That looks sort of like a pure impulse. It's not very big. It's not infinity, but it decays pretty quickly. But if it was 100 over s plus 100, that would look even more impulsive, and it would happen very quick that we would get to that 6. Here, how long are we going to have to wait before we really practically see it, the output at 6? 5 tau was right. What's producing the 5 tau? It's our filter, or it's our system. Our mode that the system produces is e to the minus 5t. We have a tau of 1/5. 5 of those is a second. So we don't have to wait very long before we can conclude that we're at 6. And if you wanted to, you could go back and look at part A and say, well, we did this before, h of s times x of s. And what's capital X of s here? Oh. Shouldn't have to wait very long. 6 over s. And you could form capital Y of s, which is h of s, x of s, do the partial fraction expansion, and get your two terms. One's constant and one's influenced by the s plus 5 factor in the denominator to get the complete response. So now you have this exponential behavior that you're used to seeing when you charge up a capacitor. That's what's happening when you're low-pass filtering a constant. And how quickly does it take to charge? 5 tau, which is 5 times 1/5, in this case, 1 second. And what did we call that before? Tau 1. That was our... So now, what if I just keep hitting you with quizzes? This is part 3. Part 3 of the quiz is what happens now if we hit the low-pass filter with this x of t. So we've hit it with an exponential, decaying exponential. We've hit it with a constant. Now I want you to hit it with a sinusoid of amplitude A, etc. What are you going to see at the output? What's going to happen at the output of this low-pass filter when you're exciting that low-pass filter with a sinusoid? What would you expect? What does your intuition or your stomach, I was going to say, it's going to wiggle, isn't it? How fast is it wiggling? So I have a 3, I have a 5. What am I wiggling with? I have a bowl of Jell-O, and I'm shaking that. So what am I? I'm exciting it with 3 radians per second. And I'm low-pass filtering that. What are you going to see at the output eventually? Will you have a transient, or will it just be shaking the whole time? Shaking the whole time. What are we going to see? Well, if you went to ECE 310 today, you could plot the MATLAB. Whoops, where's my MATLAB? There it is. This is what you would see. I don't know if that's what... Do you have 310 on Thursday? No, so see. Oh. Did you hear that Pop? Huh? Okay, what do we want to look at here? The red, if you can see it, is the input cosine. It has an amplitude of 1. And it's moving at 3 radians per second. The blue is the output. Does that look reasonable? What's up with the beginning? What's up with that? And what are you calling the beginning? How long is the beginning in this story? How long is the beginning of this story? The story never ends, but there is a beginning piece, isn't there? There's a transient piece. How long is the transient? 5 tau. You guys are just going to, no matter, you're going to wake up and you're going to go 5 tau. Were you having a nightmare? Yeah, I was dreaming about 320. 5 tau. What's tau? It's due to the low-pass filter, isn't it? That's 1/5. So we should be expecting the transient to be gone, the beginning to be gone after 5 tau. Tau is 1/5. So after a second, we've kind of hit our groove. Now we're just doing a sinusoidal steady state. And does the blue look pretty much the same period as the red? Are they aligned? Are the peaks aligned? No. There's a delay, which is our phase shift. Are the amplitudes equal? No, of course. The red is not the same as the blue. Right? Would you expect that? Yes. So now, if somebody hands you a linear system, in this case our linear system is a low-pass filter, and they excite it with a sinusoid, you know immediately what? The output is going to be a sinusoid of that same frequency of the input. How it changes or scales in amplitude depends on how that system behaves at that particular frequency. Is it going to amplify or is it going to attenuate? Depending on that system, it could do either one. And it's probably going to have some lag in that system between when you excite it and when it gets into its steady state, meaning now we have a phase shift. And that's why the peaks of the blue are a little bit shifted, delayed from the peaks in the red. So the time constant is the associated with the phase shift theta in our particular system. Now but this we could generate in MATLAB. We simply input a sine wave. I'll give you the code after class. I'm sure you don't want to see it now. You put in the sine wave, you put in the transfer function, h, and you simply say simulate. And you have to tell it to plot, but once you tell it to plot, it will give you the answers. Yes?
I apologize if you actually just misheard, but I was wondering, why is it that the first peak in blue is kind of like shorter than...
So now why is the first peak in blue not as big as the other peaks? What are we experiencing in the beginning of our story? That's our transient. So we're kind of getting to where we want to go. What did we have before? We had a transient here, didn't we? And that lasted, in this case, the transient actually lasted right here, and then we sort of locked into the input. That's what we're doing at the beginning of that blue and red input and output relationship in the sinusoid. We're trying to get into a sinusoidal steady state, but it's going to take us 5 tau, according to tau being the filter. And that's why it looked a little different. So that's why we are not yet in steady state. But in steady state, we're not changing the amplitude. That system likes to attenuate this sinusoid at a particular level at a frequency of 3 radians per second. So can we find that? Can we figure that out? And can we figure out how much delay we're going to have? Can you now tell me why the sinusoidal steady state output is going to be when I excite this low pass filter 5 over s plus 5 with that waveform? In this case, I used capital A, the amplitude of the input, as 1, so that we could quickly kind of determine what the amplitude change was. But now how do we do that? If x of t is a cosine, how did we do it in the S-plane with DC? And I've kind of given you a hint on this diagram. We looked at DC, didn't we? The origin. Now if we're exciting this system at different frequencies, we're underneath that tent. We're walking on the imaginary axis. And we're going up j omega. And if somebody wanted to excite that system with a sinusoid of 1 radian per second, they would walk up to J1 and say, okay, what's going on? What are you contributing from all of the poles and zeros? How many poles do we have? We just have the 1, don't we, in this filter. So now we're saying, oh, I hit the system with a sinusoid of 3, so I'm going to walk up to J3 and look around and basically say, who's helping or who's contributing to what's going on? It's that pole. And we had the numerator, it's stuck at 5. But now we could say, oh, how far away are you? We said how far away we were at DC. We were 5 away. This is now minus 5. Now are we further away? Yes. And where did this, so this kind of tells us how the pole is influencing the amplitude of our response, or the magnitude of our system. Now the pole is downstairs, it's bigger, so we divide by a bigger number, we're getting smaller in terms of the contribution at that frequency. And how do we have to look? If we're now standing here and looking to the positive real line and we have to turn up and look at J3 from this point, do you see the angle that you're having to rotate through? Or if I do it with my hands, we're now looking straight ahead for one arm. That's my reference. I measure relative to that and I look up at J3 and I measure that angle created by this. That's now the angle theta that this pole factor is contributing. And we also have this length, L. And you could actually figure out what the magnitude and angle of the pole factor represent in the overall, or with the overall, if you just looked at H of J3. Evaluated your transfer function at that particular location on the imaginary axis, which is J3. And what happens here? Well, I know that my transfer function, my low-pass filter, was 5 over s plus 5. I've replaced s with J3. I can do that. That's now 5 over J3 plus 5. And what can I do? Well, I can say that's a complex number. Maybe it's cleaner to think about that complex number in terms of a magnitude and an angle. And we can compute all of the different pieces and parts of that. What if I looked at the magnitude of H of J3? What's the magnitude of the numerator? So now I'm taking the magnitude of the whole quotient, but that's the same as the quotient of the magnitudes, right? So I could take the magnitude of the numerator. What's the magnitude of 5? 5. And then I can take the magnitude of the denominator. I now have 5, and if I find the magnitude of this complex number, that's just a right triangle, and we're looking for the length of the hypotenuse. And that's what you've seen here. I have one side length of 5, and the other side length is 3. And I can now find the length of that hypotenuse. Or I now can say that this is 5 over the square root of 5 squared plus 3 squared. Or this is 5 now over the square root of 34. What was that denominator at DC? That was h of 0. That was 5 over 5 plus j0. So now my denominator is a little bigger, so I'm attenuating that sinusoid more than I attenuated DC input. And this is how I change the magnitude of the input signal, by this factor. By that, how much my system amplifies or attenuates at a given frequency is determined by its magnitude at that frequency. What else can we say? Well, a complex number has more than a magnitude. We can also find its angle or its phase. What if we looked at the phase of h of j3? That's the same as looking at the angle of the numerator divided by the angle of the denominator. Or I now have the angle of 5 over 5 plus j3. That's what I'm saying. But I can we're going to pull all of these pieces apart and look at all of the zero factors, all of the pole factors, and add them up because it's easier to look at them individually. But you could plug that whole mess into your calculator if you wanted to, and it's going to give you an answer. But here we could say, oh, this is the same as the angle of the numerator, which is the angle of 5, and the angle of 5 plus j3. And you're going, what? What's the angle of 5 plus j3? Well, 5 plus j3 is a complex number. It has a magnitude and an angle. We just want the angle part. But we've already found the magnitude. That was the square root of 34. And what's the angle? So this is now, what's the angle? So this is now the angle of 5 e to the j 0 degrees, isn't it? And this one is now the angle of the square root of 34 at an angle that's the inverse tangent. Boy, can I be any angle of the angle, but I'm trying to drive home a point. How do we find the angle of 5 plus j3? We have opposite of 3 over adjacent of 5. That's the inverse tangent of 3 over 5. And how does that compare to 45 degrees? We should be expecting a little bit less than 45 degrees, right? Because we didn't have to go up as high as we went over. Just as a way to double check your calculation. So now we have, how do we do this? I have an angle in the numerator. What's the angle in the numerator? 0. What's the angle in the denominator? All right, I don't know if you picked up on that in the video, but somebody said, who cares what the angle is? And I just about threw something, but I didn't. I kept calm, The angle, so now we take all of the angles in the numerator and subtract all of the angles in the denominator. So when I say angles in the denominator subtract, do you see why? If I now said this was square root of 34 e to the j something, to find the e to the j eventually, you have the numerator j's minus the denominator j's, and that's why you can subtract the angles. So it does matter. And now if we're looking at the angle overall, we have the angle from the numerator, that was 0 degrees, and we subtract this angle from the denominator. Or, wow, I left just the right amount of space, not quite, but this is now minus 30.96 or 31 degrees. That's the phase change. So that if what we want to derive I can cut and paste in my paper, but you don't know. You've got infinite paper down below. But now what I'm going to show, what was the quiz? I said, what's the sinusoidal steady state output? We now have A. Oh, and did I ever calculate what this was? Did anyone pull out their calculator and 13? What? Square root of 34 is a little bit less than the square root of 36, isn't it? So it's a little bit bigger than 5/6. So if we do that, oh, somebody going to answer? Oh, well, we have to be careful when we're scratching, huh? So this, oh, you have a question, but this is now 0.8575 as far as a value. Question?
When we scroll down when we're talking about angles, how did we get from auto equation 5 to the j to 0 degrees because we have like an angle within an angle? How did we get rid of that?
So how did we get an angle of an angle? I'm really just saying what's the angle of this polar form? It's now square root of 34 e to the j some angle. And that angle is this inverse tangent of 3/5. So my notation may be a little sloppy or confusing, but I'm just really wanting to say you have a complex number in the denominator given by 5 plus j3. If you find that, it's going to be the square root of 34 at an angle of 30.96. Because it's in the denominator, it's downstairs, we're subtracting it. We have 0 minus 31 degrees. What we're going to then derive is that now that we know the system attenuates by this factor, 0.8575 at J3. Oh, what am I? Yeah. So now we have this, and what do we want? We now have y steady state is equal to A, and this is going to be 0.8575 cosine of 3t minus 30.96 degrees. What we want to do is figure out where that came from. And that's what we're going to say is we're going to be using h of s. If I give you now a generic h of s instead of a low-pass filter, what I want you to be able to do is say, oh, you tell me how you're shaking it, and I'm really just going to evaluate h at that frequency, j something, and that's going to determine how I impact or how I influence that sinusoid that we're manipulating. You could find the complete response. You know how to do that. So now I'm trying to derive that equation that I just showed. What are we going to assume? Well, if we excite a system at a sinusoid frequency, the only way that we're going to hit a steady state is if that system is stable. And a stable system is one that has all of its poles, all of its x's in the left half plane. It has decaying exponentials associated with it. It has e to the minus somethings. So we're assuming that all of our poles of the system h of s are in the LHP. I'm assuming we may want to text this at some point. So now we've texted it, and we're in the LHP with our poles of the transfer function. Suppose now that our input, somebody hands you an amplitude of A, a frequency of omega naught, and maybe their original input is shifted in phase. But here, make sure that all of those are consistent. If omega naught is in radians per second and you've specified phi in degrees, that's okay, that's kind of convention, but when you need to add them up, you need to convert them to a consistent unit. Radians are degrees. Here I'm saying let's keep them in radians, and here is how you could actually determine what is my actual delay. This is not the time constant. Maybe I shouldn't have called it tau hat. Maybe I should call it d or something. This is now the delay associated with that phase shift of our input. And now we've seen that even as we go through the system, we're going to have even more delay. This phi is really just where we drew our time t equals 0 line in our sketch of x of t. But what we want to now show is that this is what we end up with. We have the original amplitude of our input, that's A. We now have how does this system behave when it's shaken at a frequency of omega naught. We now need to evaluate the magnitude of that system at j omega naught. And that will scale the original input. If we put in a signal at omega naught, it's a linear system, so the system is going to shake everywhere with that same frequency, omega naught. It's not going to be shaking at the square root of omega naught or 5 omega naught squared over 7, some squirrely value. No, it's going to be shaking exactly with the same frequency that you're exciting it with, if it's a linear system. The original signal had a phase shift of phi. We changed that phase shift by how the system, it has energy storage devices in it, and so it has some delay. It's not, if we had a purely resistive circuit, then we would be lined up peak to peak. But because we have R's, L's, and C's, we probably have some delay in our system, and that's why we have to accommodate that, or that's how it enters into our sinusoidal steady state output. And all we're using in this expression is the fact that this transfer function, when we evaluate it at j omega naught, is a complex number. We're just rewriting it in polar form. We're giving it a magnitude and an angle. And once we find its magnitude and angle, boom, we can immediately plug it into this formula. On an exam, you were not going to have to rederive this. We're going to do it now. But on an exam, you can simply say, oh, I'm exciting my linear system with this sinusoid. Boom, I know that it's going to be like this, so I need to now evaluate my transfer function at that frequency. That will give you a complex number, and you use the magnitude and angle in the appropriate way. What we want to do is justify where that formula comes from. And this we've already seen. This is what's happening. And in MATLAB, as promised, you can do it like this. Here's your low pass filter. We know what its time constant is. We know it has a bandwidth of 5. The input is now going to be x of t. Oh, and I guess in that example that I just used where it was 0.3 something, I was using an input that wasn't 3 radians per second. It was closer to 12 radians per second. So if you were looking why the amplitude wasn't 0.8 something, that's the reason. Is because now I'm actually using a different frequency that's 4 pi, so I'm higher up on the imaginary axis for this MATLAB input that I've put in. Okay, so this is my frequency. It's closer to 12 than 3. So I'm way up on my imaginary axis relative to 3. And if you wanted to, you could sketch this graph, the magnitude in dB. What is our low frequency gain in this case? What was our H? How did it behave magnitude-wise at DC, at S equal to 0? What was its amplitude? 1. In dB, what's 1? You take log of 1, 0. So this is going to be 0 dB. And then how big was our filter? How many poles did we have? What was the order of our filter? 1. It was a first order low pass filter. So now we're rolling off at how fast? 20 dB per decade, or 6 dB per octave. Just depending on how you want to think about this. But this slope now and where do we start sloping down for this low pass filter? Where? At the pole. And where was our pole? I've got it in red, and I don't want it to see in red on your exam. Right? I want it to be in the ink that or pencil that you're using. You would say pole is at S equal to minus 5. Now you know you have a bandwidth of 5, and this is going to be where you break. Is the break frequency. In this example, where I said we were applying an x of f naught equal to 2, that's in hertz, so we have 2 cycles per second, which translates into 12.5, 12.6. We're rounding to 12 radians per second. Now we would go over here, and where would we find 12? Where is 12, and what is 12? In omega naught. We've identified 5 on the frequency axis. Where is 12? We're still going positive, aren't we? We're still walking in the correct direction. So 12 will be to the right. How far away? Depends on how we've sketched this, but a decade later would be 50. So if, let's say this was now 50, we now need to be at 12, and if we went an octave further, that would be a factor of 2 in frequency. So we would now say, 10 would be about right here. It would be 30% of the distance between 5 and 50, and 12 is going to be about right there. That's how we're that's where we're exciting. And what happens to the amplitude? Are we changing the amplitude when we low pass filter that 12 radian per second cosine through this low pass filter? Yes, we're attenuating it, aren't we? If we were right at 10 and this is a straight line approximation, this is not the actual magnitude curve, but it gives us a way to quickly think about it. How far down would we be if this was at 0 at 5 and we wanted to see what is our magnitude at 10? It would be an octave over, so we should be at 6 dB down at 10. So if we wanted to say, well, what is 6 dB in actual amount, we would say, oh, minus 6 dB is equal to minus 20, or let's just say this, let's say 20 log base 10 of some gain value, G. And this was now going to be the magnitude of H at J. In this case, we'll say omega naught. Can we now solve for G? Yes, it's the only unknown in there. So now this would tell us the absolute scaling amount if we were down at 6 dB. What's the scaling amount? Does anybody know if we're at minus 3 dB? How much are we down? That's 1 over the square root of 2. What's 1 over the square root of 2? Square root of 2 over 2. It's 0.707, isn't it? So now we're minus 6. It's actually 0.707 times 0.707, which is 0.5. So we're roughly at 6 dB down, we're a factor of 1/2 where we started. That would be where we would be at 10, so we're even lower than 0.5, below where we started. If we solved this for G, we would have now 10 to the minus 6 over 20. And if we go back and we say, oh, the scaling is going to be less than 0.5, if it was 0.5, we would be right here with our blue amplitude. Are we? No, we're less than that, and that's what we expect when we're even further out in frequency at 12. Wow. Derivation. This will only take 2 shakes. No, it's more than that, so I may have to fill this in later, but I want you to understand what we're doing. We're now trying to find the sinusoidal steady state output, and we know the full output is h of s times x of s for any given transfer function h of s. And what we're going to see is that we can split that complete response into 2 pieces. One piece is due to the beginning, isn't it? It's due to the transient. The other piece is what we're interested in, and that's what happens after the transients have disappeared. The transient terms are due to all of the poles in h of s. So whatever we have in h of s, that's going to give us all of these exponential decays or exponentially damped cosines and sines, whatever h of s has for its poles. That's what we will have here. We're going to throw those away and just focus on this to try to find that formula that we were looking for. Or we're trying to now inverse Laplace transform just that first piece, the sinusoidal steady state piece. So we're not trying to inverse Laplace transform all of those terms. You could do the partial fraction expansion and then throw away all of those transient ones and just focus on the one that's remaining that has the poles due to the sinusoid that we're exciting our system with. This would give us the total response. We just want to keep or focus on capital Y sub sinusoidal steady state. So now we can start going. Now we can start deriving. Suppose we're given x of t. Now what? How do we Laplace transform that? Or maybe before we Laplace transform, do you have that expression in your transform table? Wow, that was quick. So if we don't, if we just have pure sines and cosines, we're not going to have a cosine with a phase shift in our table, are we? So I'm going to rewrite this based on a trig identity. I'm going to rewrite x of t as I'm going to keep the constant a outside, and I'm going to now just say, oh, this is the cosine of the sum of two angles. Cosine of a and b, where a is omega naught t and b is phi. This is now cosine omega naught t cosine of phi minus sine omega naught t sine of phi. Or x of t is now a cosine of phi times cosine omega naught t minus a sine phi sine omega naught t, where these are really just constants. Phi is a fixed value. We take the cosine or sine of that. That's a number, and we scale it with a. This is now just a constant, as is this. They're not the same constant. That's why I'm calling them constants. But now can you Laplace transform that? If you keep these as just a constant, I'm just asking you what's the Laplace transform of a cosine and what's the Laplace transform of a sine. Or this now, you can say capital X of S is equal to, what's the Laplace transform of a cosine? S over S squared plus the frequency squared. So this is now S over S squared plus omega naught squared, but we said we had a constant of a cosine of phi scaling that. And what's the cosine, or what's the Laplace transform of a sine? It's the same denominator, it's just now upstairs we have the omega naught. And we actually have a minus, and we have this constant, a sine of phi. That's what we're hitting our system with. This is capital X of S. And if we hit it with, or if we apply this to a generic linear system, where we're calling that generic linear system capital H, then Y of S is now H of S times this mess. A cosine phi S minus a sine phi omega naught all over the same denominator. S squared plus omega naught squared. if I wanted to factor that denominator, where are the roots of that factor? Can I envision where those are located in the complex S plane? We have a voice in the back. You moved away. You used to like to be my target. Now somehow you're as far away as you don't think I have much of an arm. You're thinking correctly. But where are these roots? They're on the imaginary axis, aren't they? These are at plus and minus j omega naught. So if we rewrote this, if we wanted to, we could rewrite this as an s minus j omega naught times an s plus j omega naught. This is just another way of rewriting that denominator. And now, which of these factors corresponds to the pole on the positive j omega axis? Which of these two factors? One's upstairs, one's downstairs. The left one is the one, if you solved that one for s, you would see s is equal to j omega naught. This factor is the one that you would want to find the partial fraction expansion coefficient for. This is the one that's upstairs in the j omega axis. So this is the pole factor on the plus j omega axis. And what does this y of s, if we now wanted to do the partial fraction expansion of this right-hand side, do you see that we're going to have denominator terms associated with the capital H of s, and we already have these two factors associated with the excitation, x of t, the cosine that's shifted. But this is now just going to be our sinusoidal piece. So if we wrote y of s, the complete response, as y sinusoidal steady state of s plus y transient of s, do you see that this is coming from these poles? And this, the poles of h of s, give us our transient piece. We're assuming h was stable. All of those will just eventually decay, and they'll decay eventually based on the slowest time constant. We wait 5 of those, and we're in the sinusoidal steady state behavior. How do we write this? Well, y of s, we could now say is k1 over s minus j omega naught plus its conjugate, s plus j omega naught, plus, here I'm just going to lump all of those and say those are stable terms from the poles in h of s. Or this is consistent with our y steady state of s, and this is our y transient. Is that clear? And what we want to do now is, if we could find K1, we're pretty much done. K1 takes a little bit of pulling of teeth if we're still in the dentist office, but it's doable. But how do we find K1? This is really the cover-up method, isn't it? Because we only have one of those. So we would say that K1, we would multiply both sides by S minus J omega naught. And all of those, when we evaluate it at S equal to J omega naught, are going to vanish, except we'll be left with K1 and the left-hand side. So now we have this evaluated at S equal to J omega naught, where this is now the pole in the upper half of S plane on the J omega axis. And unfortunately, what I'm going to have to do is do this offline, fill in the final steps, and show you how we can find K1. And based on that, that's now the solution that we can now use. You hit a system with a sinusoid, how is it going to respond? It's going to have a beginning, but then we're interested probably more in the sinusoidal steady state. And we can use the magnitude and angle of our transfer function to determine that.